Good morning. This lesson forms the second part of your series of video lessons dealing with Learning Outcome 12. In the first lesson, we looked at a variety of chemical reactions in brief. Reactions that you would have come across during your education for MedSec chemistry. Basically, these are the reactions referred to in MedSec assessment criteria 12.2a, which I am reading off from over here, and 12.3a, where you should at this stage be familiar with acid-base, combustion, thermal decomposition, precipitation, displacement / redox reactions. Now we are going to discuss through this video presentation a very particular type of chemical reaction. It's a reversible reaction. Perhaps it's a concept that appears completely new. You might imagine that, but you would have already come across instances earlier on in your education in chemistry where you would have already encountered certain chemical reactions or also phase changes. A change of phase is a change of state, basically, where reversible conditions were observed. But we'll get into the particular instances as we go along. Suffice to say at this stage that we are focusing on reactions that both can move forward and once having formed the product can also go backwards and reform the reactants from the products. Let's now move on to the next slide, where we discuss the particular assessment criteria that shall be covered by this particular presentation. We shall now examine the particular assessment criteria set down by MedSec and that shall be covered via this presentation. Now, I have listed them in the order as presented in your syllabus, but this does not mean that I shall be discussing them in particularly the same order throughout the presentation. I have taken the syllabus and I have interpreted it in such a way that I feel is best for the development of the presentation and for you to understand best. So we shall be looking at changes of state, not just reversible chemical reactions. A change of state such as the one we shall be discussing, where bromine liquid can be changed into bromine gas and it can recondense back to bromine liquid. Well, that is an example of a reversible change, but it's not a chemical reaction, it's a phase change. We shall be starting off the presentation particularly with the thermal dissociation of ammonium chloride, okay, to form ammonia and hydrogen chloride. And we shall also be looking at the reversible reaction that takes place when hydrated copper 2 sulfate is heated. Okay, we shall explain how certain chemical reactions, given that they are in what we call a closed system. A closed system is a system that allows only an exchange of energy, but not an exchange of mass or amounts of substances with the surroundings. Okay? But we shall not go into the thermodynamics of what constitutes a closed system. We'll keep it simple. Just think of a closed system, I shall be repeating this at a later stage, is one that does not allow escape of any amount of the reaction particles from that closed box. Okay, they are retained inside a closed container. Okay, so we shall be examining how these reactions taking place in a closed container, okay, they may not go to completion, but they can reach an equilibrium. An equilibrium is a situation where some of the reactants have reacted to form a certain amount of the product. But then once the product forms, it goes back in the reverse direction to reform some more of the reactants. We shall see how changing the external conditions of temperature, but also if we had to vary the pressure, okay, if we also had to vary the pressure of the closed system, we shall see how such conditions will affect what we call the position of equilibrium. I shall introduce this assessment criterion in this presentation, but I shall more fully develop it in the presentation after this. Let's now go on to the next slide. First of all, there are many chemical reactions that are irreversible. So, for example, if I had to burn petrol or wax or perhaps LPG, liquefied petroleum gas, these are all examples of combustion reactions which are irreversible. Okay? Once you have formed the product does not go back to reform the reactants. However, reversible reactions are very different. The products, once formed, okay, can react together and reform the original reactants. Okay? Now, in order to illustrate this when we are writing the chemical reaction, okay, what we do is, as I have indicated in this chemical reaction at the bottom, I have used a double arrow. Now, strictly speaking, I should have used this sort of notation, but I haven't yet found this easily in the symbols menu for PowerPoint. Okay, so I'm sticking to the more readily available double arrow. But basically, whenever you see this arrow, what it means is this. Okay. Now, from this chemical reaction, we can see that ammonium chloride, all right, will, on heating, now on heating, so we can put that as a heat change, okay? I am putting heat, I am inputting heat energy into the system. It is thermally decomposed into two products, ammonia and hydrogen chloride. Now, you would have already seen this experiment demonstrated to you in the lab in the reverse format, probably when your teacher was explaining the topic on acids and alkalis. They would have demonstrated in the fume hood the reaction where if you soak a piece of cotton wool, all right, or glass wool, whatever, cotton wool is fine, in ammonia, in concentrated ammonia. So on the one side, I would have concentrated ammonia, and you'd soak another piece of cotton wool, okay, using concentrated hydrochloric acid. So let's be clear about this. We are here using the liquids, but both of these chemicals, okay, both the concentrated ammonia and both the concentrated hydrochloric acid are pretty volatile, meaning that they will form vapors of hydrogen chloride and ammonia very easily. And this is exactly what happens. The hydrogen chloride vapor moves along the hard glass tube, and the ammonia vapor moves in the opposite direction. Where they meet, now I'm not going to go into the issue of relative molecular mass and the point where exactly they meet, okay? But they will meet closer to the side where the hydrogen chloride is than the side of the ammonia. So it will be at this point where they meet approximately. Where they meet, they will join up together, and at that point they will form a white deposit, a white crystalline deposit. It would look like a crystalline deposit of ammonium chloride. It's a white line, okay? The point is this. You have gone from ammonia and hydrogen chloride to ammonium chloride. If you had to reheat that ammonium chloride, you would go back into the reverse reaction, and you could keep doing this any number of times. Heat the ammonium chloride, it will sublime, it does not melt to form a liquid, it will sublime. It will sublime to form two gases, ammonia and hydrogen chloride, which on cooling will not condense, but deposit out to form ammonium chloride again. And you could keep going any number of times. The forward reaction is brought on by heating. Okay, so you need to heat in that direction, whereas the reverse reaction, okay, where the ammonia and hydrogen chloride reform the ammonium chloride, is brought on by cooling. So we go back by cooling. Good. Let's now go on to the next slide, where we shall keep on discussing this type of reaction. There is still something else that I need to refer to with respect to this particular reaction about ammonium chloride. So basically the diagram on the left, okay, summarizes what I have already explained. You have the chemical reaction once again written out for you. However, do note that it's written out in the opposite sense. Okay, this time starting from ammonia and hydrogen chloride. Ammonia and hydrogen chloride on cooling, so the forward direction would be cooling, okay, would form ammonium chloride. Ammonium chloride on heating would thermally decompose and reform your ammonia and hydrogen chloride. I do remind you that in order to help yourselves better understand the full meaning of this chemical reaction, it is important that you make note of the state symbols and include them when you write out your symbol equation, okay, your formula-based equation. The state symbols will clearly indicate the phase change that accompanies this decomposition reaction. So heating the ammonium chloride, which is a solid, will break it down into two components in the gaseous phase. Ammonia on the one side, hydrogen chloride on the other side. And you can see how this could be done using this simple laboratory setup where the ammonium chloride is heated very gently really at the bottom of a boiling tube, and it will immediately decompose. The ammonia and the hydrogen chloride will of course escape up the tube, but if you don't heat too strongly, you will immediately notice a white deposit which will form in the top part of the tube. That's because the top part of the tube is of course cooler than the point where you're heating. So the take-home points are these two, which are highlighted at the top. Ammonium chloride breaks down when heated, we call it thermal decomposition, to ammonia and hydrogen chloride. And since the ammonia and hydrogen chloride, which are formed, can react together and form ammonium chloride again, we call it a reversible reaction. It can go in both senses, both ways. Let's now go on to the next slide, where we take yet another example of a reversible reaction, which is caused by a change in temperature. Now we shall look at the reversible change, where when you heat hydrated copper 2 sulfate, which is a blue crystalline appearance, it changes to anhydrous copper 2 sulfate. Now it's very important, even though the picture that I have used over here in the presentation just puts it in as copper sulfate, do always include the valency. So that should correctly read hydrated copper 2 sulfate and anhydrous copper 2 sulfate. I shall be explaining more about the terms endothermic and exothermic at a later stage. Don't let that concern you, okay? And I shall not explain them at this stage, but further on. All you need to know is this. If you heat the hydrated copper 2 sulfate, the blue crystals, so the forward reaction is brought on by heating, okay? You will end up driving off, removing the water of crystallization, which you have already discussed in year 9, okay, when you were doing acids, bases, and salts, okay, and which you would have later on discussed in calculations in chemistry, okay. calculations in chemistry, where you will speak of determining the number of the water of crystallization. So basically the water of crystallization is that, and when you heat the hydrated copper 2 sulfate, since the water of crystallization is not strongly bound, it is only loosely connected, if you like, it is driven off, and you end up with the anhydrous product, which is white, a white powdery appearance, and the water which has been driven off. However, do note that this is a reversible change, as can be seen in the diagram over here, and that is why I have particularly chosen this diagram. If I had to add water, okay, slowly, to the anhydrous white powder, right at the point of contact, you will notice that the color will once again change to blue. Okay, so this change is a reversible change. You heat the copper 2 sulfate and you end up with the white powder, which is anhydrous. You add the water back and you go back to the blue crystalline appearance, to the blue appearance of the copper 2 sulfate. So it can go forwards and backwards any number of times. It's a reversible reaction. Let's now go on to the next slide, where we'll be talking of a very similar chemical reaction, but this time with hydrated cobalt 2 chloride. A very similar reaction to the one we have just discussed of hydrated copper 2 sulfate is the one relating to cobalt 2 chloride. Now, this is actually used as a test for water, as also can the copper 2 sulfate be used, okay? If you add water to anhydrous copper 2 sulfate and it changes from white to blue, that means that you have the presence of water. Likewise, in this situation, if I had to add dropwise, okay, water to anhydrous cobalt 2 chloride, okay, so cobalt 2 chloride is CoCl2, okay, if I had to add water dropwise, as can be seen over here, the test strip of cobalt 2 chloride paper, which was blue is in the anhydrous condition. It turns this shade of pink when the cobalt 2 chloride, okay, connects with the water to form the hydrated compound. Cobalt 2 chloride to water. It is the hydrated form of cobalt 2 chloride. It has a pink appearance. If you have this change in color from blue in the anhydrous cobalt 2 chloride, so this will start off as blue and it will change to pinkish when it is hydrated, that means that water is present. It is actually a test for water. Now, let me note that the reaction is reversible, so I have to correct what is written over there. We'll put in a half arrow moving forward for the addition of the water of crystallization, and we'll put in the reverse arrow going back to the starting materials. This is obtained when the water of crystallization is removed, and you typically remove the water of crystallization by heating the cobalt 2 chloride. Let's now move on to our next slide. We shall now introduce the idea of a dynamic equilibrium. Now, a dynamic equilibrium is basically a reaction that is moving forward and at the same time it is moving backwards. So if I had to explain it in a very simple way, let's imagine that we have the reaction between A plus B. Okay? Now at the start of a chemical reaction there is zero product. Okay? So the reaction is going to be completely in the forward direction. If you like, it is not being balanced by a reverse reaction because there is no product yet available to go back to A and B. However, as more and more time passes and more of the product builds up, let's call the product C plus D. As the amounts of C and D build up, what's going to happen is this. There's going to be a point when as much of C and D are being made as are being removed to reform A plus B. So what we mean by dynamic equilibrium is, let's imagine that the forward reaction is like the person who is trying to run up the stairs over here. You can see that he is trying to run upwards. That is the forward reaction. So that is the speed of the forward reaction. It is how much of A and B is breaking down to form C and D. But this person is being, if you like, opposed by a down escalator. The escalator is moving in the opposite direction. And since it's moving with as much energy, if you like, with as much force as he is moving upwards, therefore he seems to be stuck. He neither moves up, neither moves down, because the rate of forward movement, the rate of upward movement in this case, is exactly cancelled out by the rate of backward movement downwards by the escalator. You could also liken it, and there is a video in a short while on this. I have introduced a video that also introduces this idea of dynamic equilibrium in a very figurative way. There is a video, okay, where you will see, okay, that a dynamic equilibrium can be compared to filling up a hole and digging a hole. Imagine the forward reaction is like digging a hole, and the backward reaction is if another person is filling up that hole with soil as you are digging it out. If you dig out the hole at the same rate as the person is filling up the hole with soil, then the hole size remains the same. The digging and the filling are taking place at the same rate. Okay? So let's go through the points very briefly. Okay? If a chemical reaction happens and the container is a sealed container, okay, we call it a closed system, okay, as indicated over here. However, if some of the products or one of the products can escape, it is an open system. Now, reversible reactions can only take place in a closed system. Clearly, if A and B will form C and D, and C and D are present in a closed system, they have the opportunity of meeting up again and reforming A and B. But if it is an open system and it allows for escape of substances, escape of mass material, then the C and D are gone. They do not have the time or the chance to meet up again and reform A and B. So at equilibrium in a closed system, okay, what is happening is that it's like an escalator or like digging a hole. The rate at which you go up the escalator is exactly cancelled out by the rate at which it's moving down. In other words, the rate of the forward reaction is exactly cancelled out by the rate of the reverse reaction. Okay? So the speed of the forward reaction is exactly the same as the reverse reaction. Like digging a hole, the rate at which you're digging the hole is exactly cancelled out by the rate at which your friend is filling it up again. They have not stopped. The forward and reverse reactions are still going on. It's simply as if you cannot observe
any change. But just because you can't observe any change doesn't mean that the reaction has stopped, which is why we call it a dynamic equilibrium. It's a balance that is maintained by all of the time A and B forming C and D. But since C and D reform A and B at the same rate, therefore there are no observable changes in amounts of either C and D or A and B. Now let's go on to the video explanation, okay, which is not in the next slide, but in the slide after that one. In the next slide, I shall be introducing what you should look out for in the video which is after that. Basically, the video will deal about this idea of dynamic equilibrium. Okay? Let's go on to the next slide. So in the video that you shall be watching on the next slide, there is, of course, first of all, the cartoon example of a dynamic equilibrium, which we can liken, which we can compare to digging a hole in the ground, a hole in the soil, if you like. If I dig a hole, that's like the forward reaction. If I have a friend right next to me who is filling up the hole, if I dig and he fills and we're doing so at the same rate, then the hole will stay the same size. It neither increases nor decreases in size. If I dig out the hole faster than he fills it up, it's like the forward reaction being faster than the backward reaction. Okay? On the other hand, if later on, whilst we're digging, he starts to fill up that hole faster than I'm digging it out, it's like the reverse reaction, moving faster than the forward reaction. Okay? You still have to get used to this idea of a reaction that can go both ways. Now, in the video, you shall first see this cartoon example to help you tune in to the idea of what an equilibrium is when we are talking about reversible reactions taking place in a closed container system. Now, also note that we refer to not just an equilibrium, we emphasize the idea of a dynamic equilibrium, because even when the concentration of products and reactants do not change once equilibrium has been achieved, it does not mean in any way that the reaction has stopped. The reaction keeps on going. It's simply that the rate of the forward reaction is exactly equal to the rate of the backwards reaction. In other words, if I am forming a certain amount of product, exactly that same amount of product is breaking down to reform the reactants back again. Okay? So at dynamic equilibrium, the rate of forward and backward reaction take place at the same rate. It can only take place in a closed system, and you shall be looking in the video at the example of this equilibrium where hydrogen gas reacts with iodine gas to form hydrogen iodide. As can be seen in this plot over here, at the start of the reaction, the hydrogen and the iodine quickly break down to form hydrogen iodide. Sorry, the hydrogen and the iodine quickly react to form the hydrogen iodide. Okay? They are making up, they are not breaking down, they are meeting up and they are forming hydrogen iodide. So the concentration or the amount or the pressure related to the hydrogen and to the iodine will quickly drop. Let's call it concentration, as is written on the y-axis. So the concentration of the hydrogen and the concentration of the iodine will quickly drop until it reaches a steady state. This is the steady state that we get at equilibrium. At the same time that they are diminishing, decreasing in concentration, what are they doing? They are meeting up and they are forming the product, which is hydrogen iodide. So initially there is a rapid decrease in the concentration of the hydrogen and the iodine, but there is a corresponding rapid increase in the concentration of the hydrogen iodide, which is the product. Notice that at the start the hydrogen and the iodine are quickly meeting up since there are many free hydrogen and iodine particles. And the hydrogen iodide is therefore being very quickly formed because a lot of the hydrogen and the iodine are meeting up to form it. At equilibrium, what has happened? Enough of the hydrogen iodide has been built up to exactly cancel out the forward reaction. The hydrogen and the iodine at equilibrium are forming hydrogen iodide at exactly the same rate that it now is breaking down to form hydrogen and iodine again. And this goes on all of the time. That's why it's a dynamic equilibrium. So once we get to this point, which is the dotted line, if you like, where you have no further change in the concentration of either the hydrogen or the iodine or of the hydrogen iodide. Notice, okay, the hydrogen iodide has reached a steady state and the hydrogen and the iodine concentrations too have reached a steady state, okay? At this point, there is no observable change either in the amount of product or in the amount of reactants. We call it a steady state dynamic equilibrium. The reaction is still going on. It's going on in both directions, but since the rate of the forward and the backward reactions are equivalent, no observable change in concentration takes place. So the concentration, as seen over here, shows you that there is no further change. Excuse me, that should be a straight line. Okay, so a horizontal line, okay, showing that there is no further change in concentration, either of hydrogen and iodine or of the hydrogen iodide. The final point to consider over here is the phase change that takes place when liquid bromine changes to gaseous bromine. That also is explained in the presentation. Basically, just as you can have a reversible chemical reaction, you can have this sort of reversible phase change. So Br2 liquid, if you heat it, it will form bromine gas, and if the bromine gas is given enough time to, if you cool it back, it will form bromine liquid again. Okay, it's a reversible change and it's a phase change. At equilibrium, in such a phase change, just as many of the bromine liquid particles will be forming bromine gas as the bromine gas particles reforming bromine liquid. So, if for example you have 100 bromine liquid particles forming bromine gas, they are exactly cancelled out by 100 bromine gas particles reforming bromine liquid. The equation is still going on, the chemical reaction, the phase change. The phase change is still happening in both directions. It has not stopped, all right? Just because there is no observable increase in bromine gas or no observable decrease in bromine liquid does not mean that the change of phase has stopped. It is ongoing. It never stops. Bromine liquid is all of the time changing to bromine gas, and bromine gas is all of the time changing back to bromine liquid. So you don't see a further increase in the in bromine gas, and you don't see a further change in bromine liquid. Now watch the video presentation, and you can also come back to this slide to clarify anything that you might not have understood in the video.
In this lesson, you will learn about dynamic equilibrium, the conditions required for dynamic equilibrium to be reached, and examples of systems at equilibrium. Imagine you are digging a hole. You got it? Imagine, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, the hole gets larger. If your friend is filling the hole faster than you, the hole gets smaller. But if the two of you are working at the same speed, there would be no change to the size of the hole. The same concept can be applied to a reversible reaction. If the rate of the forward reaction, reactants to products, is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously, even though there is no overall observable change. For a chemical system, such as a reaction or a phase change, to be at equilibrium, it must meet two important criteria. First, it must be a reversible process. Second, it must be taking place in a closed system. A closed system is one where there is no exchange of matter, only exchange of energy. An example of a reaction at equilibrium is the reaction of hydrogen and iodine in a closed container to produce hydrogen iodide. At the start of the reaction, there is a high concentration of hydrogen and iodine, and the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur. Over time, the concentrations of hydrogen, iodine, and hydrogen iodide remain constant. So what is happening here? The reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide to hydrogen and iodine. So there are no observable changes, although both the forward and reverse reactions are occurring. This reaction has not stopped, but rather has reached dynamic equilibrium. What would happen to this reaction if the lid on top of the glass jar was opened? Please pause the lesson to think about this and resume when you are done. If the lid was removed, the system is no longer at equilibrium as the reactants and products, or matter, would be able to escape the system. Liquid bromine equilibrates to form gaseous bromine at room temperature. Remember that this is not a reaction, but rather a phase change. Phase changes can also reach equilibrium under the correct conditions. As liquid bromine evaporates, gaseous bromine condenses. Since these two processes are occurring simultaneously at the same rate, there is no observable macroscopic change, but the system is in fact in dynamic equilibrium. In summary, a chemical system is said to be at equilibrium when the rate of the forward reaction is the same as the rate of the reverse reaction. There are no observable changes, but both directions of the reaction are occurring, so it is a dynamic equilibrium.
Now, in this slide, we shall discuss a further idea regarding a dynamic equilibrium, we shall introduce the idea of a position of equilibrium. And this idea of position of equilibrium is also introduced in the next video that you shall be seeing immediately after this slide. First of all, let's go through the points in sequence, okay? These are the points in sequence that you should watch out for in the video, okay? So the first thing that the video narrator underlines is that reversible reactions achieve a state of dynamic equilibrium. So as we have already indicated, okay, we can illustrate a reversible reaction by means of this view-like overall general equation, and the double arrow, okay, with the forward length of the arrow being the same as the backward length of the arrow, indicates that the reaction is in a state of dynamic equilibrium, and the rate of the forward reaction is equal to the rate of the reversed reaction of the backward reaction. It should be noted, as can be seen from the video, that when the equilibrium is achieved, okay, you could have a lot of the product, okay, a lot of the product and very little of the reactants remaining, which is, after all, in an industrial process, what you'd like to achieve, because you are not reacting A and B to remain with A and B. You'd like the position of the equilibrium to be shifted to the products. So when in a dynamic equilibrium you end up with this situation, let's use this way of representing it, with very little of the reactants remaining and a lot of the product being present, we say that the equilibrium is now shifted to the right. But notice, we still talk about an equilibrium because the concentrations stay this way. You stay with exactly the high amount of C and D, and you stay with exactly the small amount of A and B at equilibrium, okay? That is the equilibrium position. It's not in the middle. The equilibrium position favors the forward reaction. Now, if on the other hand, we have the opposite situation, where we have a lot of A and B at equilibrium, but a very small amount of C and D, we say that the equilibrium is now shifted to the left, and there is more of the reactants at equilibrium than you have of the product. Now, you can let time go by and it stays exactly at those amounts, a lot of the reactants and very little of the product. It does not mean that the reaction has stopped. This is the position of the equilibrium. The position of the equilibrium happens to favor the reactants. It is, in other words, shifted more to the left. Okay? So, this shift in position of equilibrium, whether it is to the right or whether it is to the left, can also be affected by changing conditions such as temperature or pressure. But we shall discuss how an equilibrium position can be changed in the next video presentation. Okay, so this is where I stop. After you have seen the video on the next slide, that's the end of this presentation, where we've discussed the idea of reversible reactions, which also are not just limited to decomposition reactions, such as we saw from hydrated copper 2 sulfate to anhydrous copper 2 sulfate. But reversible reactions also include phase changes. And we saw that, for example, the changeover from bromine liquid to bromine gas and bromine gas going back to bromine liquid, whilst not a chemical reaction, it is a change in phase and it is a reversible change, and it also can achieve a position of dynamic equilibrium. Okay? We then moved on to explore this idea of dynamic equilibrium, what exactly it means, where the rate of the forward and the reverse reactions are equivalent. It's like running up an escalator that's moving down at the same speed that you are running up, so there is no apparent progress, but you are still running up, you are still consuming energy, and it is opposing you in the same time. So you're not stopped, no one is stopped, neither you nor the escalator, all right? You're both moving, but you are moving at the same rate in opposite directions. It's like filling a hole and digging a hole. I dig a hole with a certain rate, my friend fills up that hole with the same rate. The rate of the forward and the rate of the backward reaction are exactly cancelled out. Dynamic equilibrium. But we also spoke about position of equilibrium. If at equilibrium you have a lot of the product and very little of the reactant, we say the equilibrium favors the forward reaction. It is shifted forward. On the other hand, if you have a lot of the reactants at equilibrium and little of the product, it means that the reaction is more shifted over to the left-hand side, more shifted over to the reactant side. The equilibrium is there. As much of the product is being made as is being decomposed or broken down or changed back to reactants. So the reaction has not stopped, okay? See the video on this slide, and then we'll keep on going with the discussion in our next presentation. Thank you for watching and have a fine day.
In today's video, we're going to look at reversible reactions and see what we mean by the terms equilibrium and the position of equilibrium. Now, most chemical reactions look something like this, with the arrow in the middle pointing to the right, to indicate that the reactants can turn into the products. This means that it's a one-way reaction. Once the carbon dioxide is formed, it won't break back down into carbon and oxygen. In other reactions though, like this one here, we have a double arrow, which tells us that the reaction is reversible. The top arrow tells us that ammonium chloride can break down into ammonia and hydrogen chloride, which we call the forward reaction, while the bottom arrow tells us that the ammonia and hydrogen chloride can also combine to reform the ammonium chloride, which we call the backward reaction. So because both of these can happen, we call it a reversible reaction. Now, the important thing to understand is that the forward and backward reactions can take place at different rates. At the beginning of the reaction, there'll be loads of ammonium chloride, but no ammonia or hydrogen chloride. So the forward reaction will be really fast, but the backward reaction won't have started yet. As the reactants turn into products though, the forward reaction will slow down and the backward reaction will speed up. After a while, the rates will even out, and the forward and backward reactions will be going at exactly the same speed. At this point, the concentrations of the reactants and products won't change anymore, so we can say that the reaction is at equilibrium. So to clarify, at equilibrium, both reactions are still happening, but they effectively cancel each other out. So there's no overall change in the concentrations of the reactants or products. Of course, in reality, the molecules are still breaking down and reforming, but because they do so at the same rate, there's no overall change in the concentrations. Now, something to point out here is that just because the concentrations of the reactants and products are constant while at equilibrium, does not mean that they're the same as each other. For example, there could be lots of ammonium chloride and only a small amount of ammonia and hydrogen chloride. Or there could be lots of ammonia and hydrogen chloride, but only a small amount of ammonium chloride. In either case though, as long as the forward and backward rates are the same, then the reaction would still be at equilibrium. However, what would change when we have these different concentrations is the position of the equilibrium. When there are more products, like this, we would say that the equilibrium lies to the right. But if we had more reactants and fewer products again, then we'd say that the equilibrium lies to the left. This position of equilibrium can change depending on the conditions. For example, adding heat to this reaction encourages the forward reaction, meaning we'll have relatively more products, as the position of equilibrium moves to the right. On the other hand, if we cool the conditions of our reaction, it would push the position of equilibrium back to the left, so it would have more ammonium chloride again. Regardless of its position though, equilibrium can only be reached if the reversible reaction is done in a closed system, which means some kind of sealed environment from which none of the reactants or products can escape. Because if the products kept escaping, it would never reach equilibrium. The last thing we need to cover is that reversible reactions are always exothermic in one direction and endothermic in the other. For example, in this reaction, which shows the thermal decomposition of hydrated copper sulfate to anhydrous copper sulfate and water, the forward reaction is endothermic, and so the backward reaction is exothermic. If you're not familiar with these terms, hydrated just means that water is present, and anhydrous means that there's no water. Now, because the forward reaction is endothermic, it requires heat energy from the surroundings to work. So if we were to heat some hydrated copper sulfate, which exists as blue crystals, it would drive the reaction to the right, which evaporates off the water and leaves white anhydrous copper sulfate powder. If we then took away the heat and added some water to this powder though, it would drive the backward reaction, so the equilibrium would shift to the left and reform our blue crystals of copper sulfate. And because this reaction is exothermic, it would re-release all of that energy it had just absorbed in the forward reaction. So to quickly recap everything, reversible reactions are those with a double arrow in the middle, which shows that they can react in both the forward and backward directions, one of which will have to be exothermic, and the other endothermic. And if these two rates are the same, then we say that the reaction is at equilibrium, and the concentrations of the reactants and products will remain constant. The position of equilibrium can change though, and will shift to the left or the right depending on the conditions. Anyway, that's all for today, so hope you enjoyed it, and we'll see you next time.